everyone. In this video, we're going to begin our discussion of second order linear equation. Second order means that you're going to have a derivative, you're going to have a second derivative, so y prime, or you could write that as d squared y dx squared. The x could also be t, and you should know that the y and the x are interchangeable, depends on the variables. This is second order. And then linear just means that when you have a function, it's going to be in terms of, let's say it's differential equation of y, it's going to be in terms of y double prime, y, and other successive derivatives of y. It's not going to have something like sine y. It's not going to have something like this. So it should just be linear in y prime, y double prime, and all the derivatives of y. Homogeneous equations with constant coefficients. So it's the same thing as that, except they're going to be homogeneous. And homogeneous just means that it's equal to 0. Okay, so as you can see, it's y prime, y double prime. You don't see like sine of y, anything like that. So this is linear. Since it's going only under the second derivative of y, this is second order. So this is a second order linear differential equation. Now we want them to be constant coefficients. So that just means a of t, b of t, c of t are all going to be constants. So they're not going to be like 3t, it's just going to be maybe 1, 2, 3, something like that, constants. And homogeneous just means that d of t is going to be 0. If a of t is 0, it's not really a second order linear differential equation, it's going to be first order because this is just 0. Right, so a of t cannot be 0 anyway, so you can just go ahead and divide it by a of t. Divide everything through by that and you'll get y double prime plus b of t over a of t, we can call that lowercase a of t. C of t over a of t, we can call that lowercase b of t. And then d of t over a of t, we can call that lowercase c of t. So that's what our equation looks like now. And for it to be homogeneous, we just want to set c of t equal to 0, d of t equal to 0, same thing, right? So you just want the right hand side to equal 0. Questions? The first one we'll do is actually a very simple example. We'll just do this, and it's going to be a bit of a thought experiment. So let's see if you can find a solution to this. Y double prime minus y equals 0. And there are a number of ways of going about doing this. You can think about it, just what does this represent? It means there's some function, that second derivative minus that function is 0, meaning that the function is equal to the second derivative. So y double prime is equal to y. And is there a function that meets this criterion that you know of? And if you think about it, there is one function that has every derivative of it equal to itself, and that function is y equals e to the x. It's known for having the same derivative, e to the x. The derivative of that is just e to the x. So we know that's one solution. Is there anything else? Well, you might be tempted to think of sine and cosine, but remember, sine of x will have a second derivative of negative sine of x, cosine of x will have a second derivative of negative cosine of x. So it's not quite that. But we can take inspiration from this. What if you just make that a negative x, e to the negative x? So let's say y1 is equal to e to the negative x, then y1 prime is equal to negative e to the negative x, and y1 double prime is going to be negative e to the negative x, which is e to the negative x, and y1 is equal to y1 double prime, as you can see, right? E to the negative x, e to the negative x. So that's another solution. And let's say over here that we want our solutions to be of the form. Over there we saw e to the x, e to the negative x. In general, that's just e to the r x. And actually, let's go with t. It's more standard over here to go with t. You might see that in a textbook. So we just, instead of x, we just deal with t. So we just say our solutions are going to be of the form
y equals e to the rt. Okay, that being said, we can just plug it in. We know y is e to the rt. What is y prime? That's just going to be r e to the rt. What is y double prime going to be? Right, y double prime is going to be, we put another r in front, so it's going to be r squared e to the rt. We can now plug all this stuff in.
We know that y double prime is r squared. So it's going to be a r squared e to the rt plus b times r, so b r e to the rt plus c times e to the rt equals 0. It looks a little complicated here. It looks like we've just made our work even more challenging ahead of us, but luckily for us, we see that there's this common e to the rt, e to the rt, e to the rt factor in each of the terms. And we also know that e to the rt can never equal 0 because e is a positive base, and no matter what the exponent is, it's never going to equal 0. which means we can divide everything by that. And when we do that, we just get AR squared plus BR plus C is equal to 0. And this thing that we got over here, this AR squared plus BR plus C, this is known as our characteristic equation. And when we see this, what type of equation is this? Well, it's just a quadratic equation. We know A, B, and C are constant coefficients. We were given that already. So when you're actually given this in a problem, you can easily find the roots R1 and R2. And that's another interesting thing. There are going to be two roots, right? For any quadratic equation, there will be two. Of course, they can be the same. Sometimes they can be real, complex, something like that. No matter what happens there, you will end up using these same roots in some form in your answer. And the most simple case of that is what we're going to continue discussing here. We're going to say that our roots are R1 and R2. And let's assume for now that they're both real roots and they're both distinct. Okay, and that doesn't have to be the case because there are a few other cases as well. You can have both roots being the same. You can have both roots being complex and distinct. So there are a few different options here. But over here, we're just going to assume that R1 and R2 are different. So R1 is not equal to R2 and R1, R2 belong to the real numbers. What did we say in the beginning? We said e to the RT. We know that R1 and R2 work, so e to the R1t should work, right? Y can equal this. Y can also equal e to the R2t. Now, is that all y can equal? Why don't you go try this yourself? What if y were equal to e to the R1t plus e to the R2t? It's going to be a bit difficult. It will take up a lot of space and it will be a little messy. But go ahead and plug this in. Find y, y prime, y double prime. Write out this equation and see if it holds true. And once that holds true, try something a little bit more challenging, one extra layer to it. Y equals C1, some random constant, e to the R1t, plus C2, some other random constant, e to the R2t. Go ahead and put this in and see if it works out the same way. And what you'll see is that it does indeed work out. This over here is a linear combination. Okay, that's all well and good. We know now that we can find e to the R1t, e to the R2t. How do we find these roots? Well, we find the characteristic equation. You just replace, essentially to get the characteristic equation, you just replace the y double prime with r square, y prime with r, and y with just a 1, right? It's just, you remove the thing there. You find R1 and R2, assuming of course that they are both real and distinct, right? So that's the assumption that we have here. And then you find this. Now how do you go ahead and find C1 and C2? You need to use the initial conditions. Notice that I say initial conditions, not initial condition. Because when you're, first of all, there are two separate constants here. So that might already suggest to you that we need two initial conditions. Also, like we saw here, that two R's. This is a second order thing. So in general, for an, well, let's stick to second order for now. For a second order differential equation, there will be two solutions. It says e to the R1t, e to the R2t. And then any linear combination of that. And then you need two initial conditions if you want to get an IVP. Okay, IVP solution. So now that's a lot of stuff. So to really reinforce that learning, let's go ahead and do some practice questions, which we'll do in the next video. Thank you for watching.